So in this particular section, what we're going to look at is the galvanic or voltaic cell. And I took your suggestion and changed all the text to black, so maybe it'll show up a little bit better. But basically, when you talk about a battery, whether it be a battery in a calculator or watch or wherever you're going to find a battery, it's an electrochemical reaction. You're taking a redox reaction and you're capturing the electrons that are produced. Redox reaction, something gets reduced, something gets oxidized, and that's a transfer of electrons. And we put it together in a system where we capture those electrons or connect it and make a complete circuit, then we have a galvanic cell. They also call them voltaic cells, depends on which textbook you're looking at. The two most popular textbooks in college right now are Zumdahl's, and the one that I have over here called Brown and LeMay and somebody else, I can't remember their names. But the Brown-LeMay textbook and the Zumdahl textbooks are the #1 and #2 sellers. So they're going to be out there. The Brown and LeMay call them voltaic cells. Your book calls them galvanic cells. So it's the same thing. So when you get to that point, you understand what they're talking about. So we're taking oxidation reduction reactions, and if you connect these things together with some wire, there's going to be a flow of electrons. Electricity is a flow of electrons. And so what happens is, in this particular case, zinc is going from the element to zinc plus 2, so this is losing electrons, and because it's losing electrons, a lot of the zinc is going to go from the solid strip into the solution. Doesn't make sense because they got copper ions in the solution. I don't think that's quite right. So this is going to be zinc and probably zinc sulfate solution or something like that, but that's what's happening. So if you actually mass this little electrode right here, at the end of the reaction, it's going to weigh less because the different atoms, the metal atoms, are going to lose electrons, become ions, and they're going to flow into the solution. Over here, if we have a copper electrode, what's going to happen is the copper is going to grab those electrons and it's going to plate out. So you can see on this one right here, the color of the solution is getting lighter, and you can also see where it's plated out on the electrodes. If you have car batteries or things like that, you can actually go and open one of those up very carefully because you got sulfuric acid in there. But if you can look at them of an old battery, a lot of the plates in there have this stuff built up on them because it's the lead that's in the solution that's plating out. But that's the basic galvanic cell. And if we take that galvanic cell and we connect the two pieces with some electric wiring, those of you who have looked at Lydia and Audrey and Kim's little experiment that they've been doing back there, they were actually building a galvanic cell. And what they're trying to do is come up with a way of making it more efficient and making it able to drive things and move things. We're still limited by the chemistry, and we're still limited by the types of materials we have. But basically, you're going to get a flow of electrons. Now, this particular picture is a true galvanic cell. If you look at that little device right there in the middle, that's called a porous disc. There's two different ways that you can make the circuit complete. One of those ways is what they call a porous disc, and that's just a device that allows the complete flow of electrons, ions, throughout the entire circuit. There's another one which we call a salt bridge, and I'll show you one of those in just a minute. But the whole idea, if you hook this thing up without a connection between the two cells, it's going to give you a burst of electricity and it's going to stop. Because what happens is you're losing electrons in one side, they're gaining on the other side, but then you've got a charge, you've got a polarity there, and there's nothing that connects that polarity and makes it a complete cycle. So you have to have that complete cycle. It's all such a setup, a galvanic voltaic cell. I prefer voltaic. I don't know, it just sounds a little bit more interesting to me. All right, so here's your standard cell, and one of the things on AP questions they're going to ask you to do is to draw a voltaic cell or a galvanic cell. So when you do that, you're going to sketch a beaker and a beaker. You're going to put a couple of cathodes in there. Always put in the salt bridge. This is the salt bridge, which is basically a glass tube, and they put a kind of a gel in there. Sometimes they'll stuff that glass tube with cotton, and then they'll put in some type of an ionic substance in here. And in this particular one, I think it's sodium nitrate is what they're putting in there. But what that does is that allows the complete circuit for the electrons to flow through that whole thing. You can connect the wires to the cathode and the anode. That's what these things are called here. You're probably going to have to identify what the solutions are and what the cathode or anode is made out of in order to do this. We have our basic, come on, go over there, move. It's not moving. Okay. What we have is our basic redox equation down here that's been written with the electrons still in. So it's not totally balanced because the electrons are going to cancel each other out. So we're having the zinc getting, yeah, here we go. This is the half reaction for the zinc. This is the half reaction for the copper. So they're having the two half reactions written down there. And these are going to be really easy when we get to looking at the table, really easy to do. Key to a lot of this is understanding what's happening and in which one. And I have the note up here. The anode is the negative side. So when you look at a battery, if you pull out a battery, you got a plus and a minus. The minus end of that battery is called the anode, and that's where oxidation happens. And the mnemonic device I have, the book has a different one, but the one I use is anox. In the book, they talk about anode and oxidation both have vowels at the beginning. So it's a little mnemonic device to help you remember. Reduction is going to occur over at the cathode, and I use the idea of a red cat. Red for reduction, cat for cathode. So red cat, cathode, that's where reduction is going to take place. And on the battery, it's going to be the positive pole. Okay? And let's see, the other thing you need to make note of is the flow of the electrons, because they want to know which way the electrons are flowing. And they're always going to flow from the anode to the cathode. Unless we do electrolysis. Electrolysis is actually the opposite. We actually put a battery in the system and drive it in the other direction. Because electrolysis is plating different precious metals on pieces of lead or something like that. So you come up with these wonderful, glitzy 24-karat gold plating on there. Yeah?
Is that how you charge rechargeable batteries?
You charge and recharge batteries by doing the same thing. You're going to put a battery or a power source in there, and you're going to drive the electrons in the other direction. And that's going to build up the charge in the battery. So that's the same principle. Yep.
Why does the zinc flow from the anode, but the copper flows into the cathode?
Okay, what's happened here, this is the anode side, so this is where oxidation occurs.
Okay.
Okay? And oxidation means we're losing electrons. Lose electrons, oxidize, Leo, right? So this is zinc metal. When zinc metal loses 2 electrons, it becomes the cation with a +2 charge. So what it's showing here is showing that the cation is being formed from the metal. That's what I said a minute ago. This particular piece of zinc, it's going to lose mass.
Okay.
You can mass this and then run the experiment and then go back and remass it, and it'll lose several grams in that process
So
before it runs out.
Is copper going to gain mass?
Then copper is going to gain, and so over here, this solution is copper sulfate, or copper nitrate here, I guess. That color, real dark blue, is going to get fainter and fainter and fainter, and also this cathode over here is going to gain more mass, so it's going to have more copper on it.
Okay.
Now, if we put the same solution in here and then just put a piece of, real cheap metal, what we can then have is a piece of cheap metal which is covered in copper. So we have this nice little
Copper
cover.
blended.
That's called electrolysis.
And that's
Mr.
not
Liller,
like
how about that?
making.
Huh?
Is that like making an element?
No, no, we're not making any elements, we're
Okay.
just taking the element out of solution and plating it on
Okay.
in the solid form onto a, some kind of a base or something like that.
Is that how
Like a
they
piece of
make
metal or
games?
something.
Can we do this experiment after the test?
I have a setup back there that we can actually,
We should do that.
if you'd like
We
to.
should do that.
Yeah,
Yeah.
we should.
How long
I've
does
got
it take?
probably 6 or 7 different kinds of electrodes.
Making copper.
And how long does it take for this to occur?
If you set up a galvanic cell with our sensitive balances there, from the start of the period to the end of the period, you'll have a noticeable, you can actually see the amount of metal being plated out on it. So it happens pretty fast. So we're going to construct a galvanic cell. This is a good example of how these problems would show up on the test. Okay? So they're going to give you a reaction, and then they're going to ask you what's being reduced, what's being oxidized. So you assign all the values on there, and we know how to do that. So in this particular reaction, what is being reduced and what is being oxidized would be part of the real easy part of the test question. So you can do that. Then you're going to figure out which direction do electrons flow. Well, all you have to do is figure out what's the anode, what's the cathode, and it's going to flow from anode to cathode. And once you know what the anode is, Drew, then you
Will
can
it
figure
not-
that out.
Will it
Huh?
not flow in the direction of the reaction? Or is it something?
It's going to flow from the anode, whatever the anode is that you're starting with, to the cathode.
Okay.
And my notes are all messed up here. Okay? Here we go. Another way of phrasing that is it's going to flow from the reducing agent to the oxidizing agent. Now, I already gave you a mnemonic device to help you remember what this one is. Which electrode is the cathode, which electrode is the anode?
Red cat.
Red cat.
Reduction is cathode.
Anox, and a red cat. So you find out where the reduction is. So it's very important to get these first two parts right so you can get the other parts right. And that's probably a third of the type of question you'd get. So if you got a free response question on electrochemistry, you're going to be looking at something very much like this. Now,
Can you walk through this?
the challenge is to draw a galvanic cell. Okay? So here's my little drawing of a galvanic cell and the answer to that question. So electrons are going to flow from the reducing agent to the oxidizing agent. Oxidation occurs at the anode. So here's our anode. This is where oxidation is going to occur. Anox. The electrons are going to flow from the anode to the cathode. And what they usually recommend you doing is just using little arrows, drawing the line, put little arrows on there to show how that's done. Reduction is going to occur at the cathode. In this one, I've also put in the
What happened to the little tube where there was another tube?
phosphorus gets oxidized and the manganese gets reduced. I'm sorry, Bobby?
She wanted to know what happened to the middle tube, but that's.
Okay, this would represent that salt bridge or represent that porous disc.
I know
You
we
have to
just,
have a separation between the two of them.
we're
So
just
it-
assuming that they're switching places.
Do what?
Do we just assume they're switching places with each other?
What's switching places?
Nothing.
I'm not
Yeah.
following you.
Well, the NO3 was flowing from. hold on. Never mind.
Okay,
Confused myself.
Justin?
What are the two metals?
Usually they put in,
Will they
Yeah.
tell you what two metals it
it
is?
depends. I mean, you can use different metals, and I'll talk about the entire reduction potential list. And so these are the metals that are generally used. And does anybody know what a lithium-ion battery has in it besides lithium?
Battery.
Ions.
I used to.
Anyway, that's a different question altogether.
Can we have the answer?
I don't know what the answer is. I just asked you.
Was that one of those questions that you actually were asking us, or was just one of those?
That's the question I'm asking you because I don't know the answer.
Did you watch Big Bang Theory last night?
No, I worked on this. All right,
Which episode was
so we now have an idea. Any other questions on how to do this? Draw galvanic cells, things
Can
like
you-
that?
Hold on, so I can draw
Okay.
that.
So
Is that, sorry, go ahead.
Question?
Go ahead, Bobby.
So we don't have to label the thing anymore, they just know.
Label the thing with
The salt bridge.
the salt bridge? No, you don't have to label salt bridge. Number one, the question didn't give you enough information to know what is in the salt bridge. But basically, it's an ionic substance. And the first one I think we looked at it was sodium nitrate. And what it is, it's something that goes into solution and does not react with anything else. So it's going to be potassium or sodium because you can put those in a solution. They're going to completely dissociate. The nitrates, it's going to be something like that. And the whole purpose of that salt bridge is so that you don't have a buildup of electrons in one side. So if this was two separate systems, there was nothing in here, as soon as I connected the wire to it, we're generating electrons.
Yeah.
And as soon as you generate electrons, it goes through that wire and boom, it ends up over here. And you got a ton of electrons over here, and you got a lack of electrons over here. It's not going to run anymore. So that salt bridge allows the current and the ionic substances that build up to bond with something else to keep the circuit going, keep electricity being produced.
So technically, if you make that a full circle, that's.
That would be a galvanic cell or a voltaic cell.
Okay.
It has to have that circle, it has to have that completion. Just like if you know, if you've ever looked at electricity before or anything like that in any classes, if you got a wire connected, you have a circuit. If you have a break in the wire, a fuse goes out, an instrument's not working, that's called an open. And you have an open, the electricity is not going to pass through. And a lot of times people, electricians, will figure out where that open is and go in and mend it. Because that's an open, and open means the electricity's not going to flow, the electricity's not going to flow, whatever you've got's not going to work. So you have to have that.
So is that an acceptable drawing on the text?
I would say that would probably answer all the questions. Let's go back and look at the questions. Did I identify what's being reduced and what's being oxidized?
Yes.
Did I show the direction of the electrons flow?
Yes.
Did I talk about which electrode is the cathode and which electrode is the anode?
Yes.
Yep.
Okay.
Okay.
So we got all of our information there in a fairly easy, readable manner. All right? So, we're going to construct a galvanic cell based on this reaction. This is a little bit of a practice for you. Draw a galvanic cell and identify the components. We have
Bless you.
zinc plus 2 and aluminum 0, going to zinc 0 and aluminum plus 3. So write that down, draw a galvanic cell, and answer those questions. You can stop.